So I think we should start. This is the fifth time I've had the privilege and pleasure speaking at Coroutine. And for me it's a bit of coming full circle because every year I'm speaking about different subjects, but today I will revisit the same topic as my first Coroutine talk from about 4 years ago. I'm on Oracle's Java Platform Group, which means I work on OpenJDK here in London as the technical lead for Project Loom, a project that aims to add continuations and lightweight threads to Java, and later also tail call elimination. Now, I've given quite a few talks on this subject, and each one is different. And given that this is Coroutine, a conference with a certain focus on programming languages, this particular talk will be from a programming language design perspective. This is a bit ironic because not only am I not a programming language person, I'm a programming language skeptic. This means that I think that we are already seeing diminishing returns in our ability to deliver significant capability boosts through linguistic features. Of course, this is not black and white, and there could be some problem domains where there has been little progress so far, and perhaps there are still low-hanging fruit to pick. But perhaps this is not too ironic, because I work in Java, and I believe this perspective is compatible with one of Java's most fundamental design philosophies. So first, before we go on, I'd just like to make sure we're on the same page with regard to what Java is. Java is a specification, or more precisely, a few specifications. We use the name Java to mean both the platform, which includes the virtual machine and the standard libraries, as well as the Java language that is used by most, but not all, the people who target the platform. Usually when I say Java, I mean the platform, not the language, but if I mean the language, I will try to make that clear. So while Project Loom will eventually become part of the Java specification, we do our development as part of OpenJDK. OpenJDK is the name of Oracle's implementation of Java. It's open source. Oracle leads the project and contributes the vast majority of development, but many other companies contribute as well. These are just a few of them, and several companies provide binary distributions of the JDK built from the OpenJDK project, from the sources. And this is as good a time as any to show the slide saying that because I work at Oracle, everything I'm about to say is possibly a lie. Okay, James Gosling, Java's original designer, described the platform as a wolf in sheep's clothing. He realized that what developers really needed and wanted were good JIT compilation, dynamic linking, garbage collection, and low overhead serviceabilities, its profiling, etc. Areas where Java continues to lead the pack to this day, but these things are hardly linguistic features. He'd hidden those features in the runtime, the Java virtual machine, and that was the wolf. And he packaged it and presented it, wrapped in a language that, at least at the time, in 1995, was considered familiar and non-threatening. If we dig in deeper, we can contrast Java's design philosophy with a different one called Zerocost abstractions. This is a philosophy perhaps most associated with C++. The philosophy of Zerocost abstractions really means that you pay in performance costs, based on the abstraction you choose when you write the program. So those circles are abstractions. They tend to be rather narrow, and the squares are the instances, and let's say the color represents the cost. And you need to pick which one you want, and you know which price you're going to pay. And you need to pick those when you write the program. But there is a drastically different approach, which perhaps I would call zero-cost instances. And that one is, generally speaking, the approach taken by Java, at least where possible. The idea is that you use fewer but wider abstractions, and the cost is determined for each use site according to what the runtime determines is necessary. Perhaps the most classic example of the two approaches is that of subroutine dispatch. In languages following the zero-cost abstraction philosophy, like C++ and Rust, there are two kinds of function calls, static and dynamic. And the programmer chooses, when writing the code, which one of them they need, dynamic dispatch being the more expensive. On the other hand, in Java, which follows the other philosophy, there is only one kind of function dispatch. Semantically, it is dynamic dispatch, but whether or not you pay the actual cost of the dynamic dispatch is determined by the runtime, thanks to the JIT compiler, on a per use site basis. If a specific use site only ever calls a single target, the JIT will devirtualize and inline the call, and the cost is that of a static dispatch. And if it's another use site, the call has multiple targets, then that particular site will pay for dynamic dispatch, even if at both call sites the call is to the same function identifier. Now, there are many details involved, and neither picture is entirely accurate, but roughly speaking, this is what happens. Both of these designs have very significant advantages and very significant disadvantages. And I believe that neither of them dominates the other, but it's possible that each is more appropriate for a particular domain. Zero-cost abstractions is perhaps more suited to domains that require a great degree of control, such as constrained environments, maybe like embedded devices, and in such domains, the great accidental complexity that they add is less accidental, because fine-grained control over the hardware is essential to the domain. On the other hand, zero-cost instances is more suited to domains that have greater functional complexity, but are less resource-constrained and can do without fine-grained control. Because the zero-cost abstraction approach gives the developer fine-grained control over the hardware, and the developer must communicate their choice to the compiler, those languages usually focus more on linguistic features, while the zero-cost instances approach focuses more on the runtime. And indeed, Project Loom will attempt not to entail any language changes and introduce no new abstractions, at least not at the language level, only new implementations. But let's not kid ourselves, design philosophy is nice, but ultimately we need to deliver something satisfactory and at an acceptable cost. So implementation challenges also play an important role in feature design, and we'll talk about those as well. Okay, so now let's closer to our actual problem, but we'll start with some theory. Our view of computation has changed over time based on what we use computation for. Traditionally, we used to think of computation as being deterministic. The circles we see represent program states, and on the left we have deterministic computation. We don't know in what state we start the program, because you can think of it as starting the program with different command line arguments. But once we do, there is only one outgoing edge for each state. Once we start, we know where we're going to end up, and this view sees computation as sort of a function. You have an input and you get an output. In the last few decades, we've been using computation more and more in interactive systems. And such systems are non-deterministic, intrinsically non-deterministic. And if we are at any point in the program, the next state could possibly be more than one. One of the reasons for that is interaction, or I/O. And that's the one we are mainly going to be talking about. For example, if you want to read an input from the user, or read some packets from a socket, you don't know in advance what it's going to be. So you don't know what the next program state is going to be. If you store it in a variable, it affects the program state. There are other sources of non-determinism like multi-threading, etc. And we're going to talk about how different languages do I/O. I'm going to start with a paradigm that is perhaps most closely associated with the deterministic view of programming, pure functional programming. In this paradigm, a language term, like a subroutine application, behaves similarly to a function application in maths. For any given value of input, you necessarily get only one and always the same output. So the question is, how do we describe non-deterministic programs that arise due to I/O? One way to do that is based on the following observation. We can think of a coin toss, and not necessarily even a fair one, as being non-deterministic because we don't know the outcome in advance. But this view is still compatible with the belief in a deterministic universe. So how can that be? Because in a non-deterministic universe, the outcome is perhaps unknowable in advance with the right, is perhaps knowable in advance, but only with the right machinery, but not to us if we don't know all the parameters, like balance of the coin, the strength and point of impact, the air resistance, etc. So if I say that I will non-deterministically turn my head left or right then from your perspective, the situation is exactly the same as if I said that I will turn my head left or right based on an instruction that someone has written and put in a locked box that you would then pass to me, but only if I have the key to the box, but you don't. If you also have the key to the box and can look inside before you hand it to me, then from your perspective, the two situations are no longer equivalent. So we can replace the non-deterministic view on the left with an equivalent one on the right just by adding arguments. And it will be equivalent as long as we can't directly inspect the value of those parameters, that they are opaque to us. So we can model non-determinism, future behavior that can take multiple paths, as deterministic functions of additional opaque arguments. The language perhaps most associated with the deterministic style is Haskell. What you see here is not Haskell. It's a language that I made up for the purpose of these slides, but it's very similar to Haskell. And we're going to try to express non-determinism in the way I just described. So we have some I/O subroutines. Get line to read input from the console, and put string line to write some out to read input, put string line to write some output. And they're going to take this mysterious opaque parameter called world. And world will represent the state of the universe, the stuff affecting, like the outcome of the coin flip, but unknown to us. And these subroutines are going to consume it and give us a new value of the world, as well as perform the I/O operation. So get line is going to read a line, read a string, and put string line is going to output. So in this language, the main program just takes the state of the world and returns the state of the world. I've used a construct that doesn't exist in Haskell Trek, just so that I could reuse the W variable, but this is how we would like it to look. The important thing here is that we cannot inspect the value of world. The only thing we can do with it is pass it to I/O routines. So to see what's going on more closely, I've changed the names I've given to value. Instead of reusing the same W variable, I've used different ones. So I start with W0, I consume it in get line, get W1, consume that, input string line, get W2, and then I'm done. But here we see that this isn't sufficient, and in fact this won't work to represent I/O for the following reason. Every time we read a line from the user, we want to model it as a function of the world parameter we give it, and we don't know what the state is going to be. So if I use W0 twice, in this model I should get the same result twice, but that does not model user behavior because the user is allowed to input different strings at the two different times. So one way of solving that is with something called linear types, and they are represented with the upside down exclamation mark. If I say that world is a linear type, then the compiler is going to ensure that we only use each of those values exactly once. So if I pass W0 to get line, and then I try to pass it again, we're going to get a compilation error saying that W0 has already been consumed. You can think of it analogously to the way that even if you were not allowed to inspect the box that you passed to me, if you could somehow clone it, then I would no longer be non-deterministic because you know that every time you give me the box with the same clone, I'm going to do the same thing. But if you're not allowed to clone me, if you're only allowed to pass it to me once, then combined with the fact that you can't look inside the box, that is sufficient to model non-determinism. And that is what it's going to look like. Now, of course, Haskell does not do this. There are research languages that do. One of them is called Cogent, if you've heard of it. Another, I think, Idris is experimenting with that solution. I think it was presented in the previous talk. But Haskell does something different. So there is another solution. And if you remember, I said that even in the deterministic model, there is one point where we allow non-determinism, and that is the beginning of the program. We don't know which state we start the program in. You can think of it as a command line argument, but once we start, we must continue deterministically. So what we can do is to move non-determinism to the beginning of the program, outside the program itself, and say, okay, so we start from A, we do a deterministic transition to B, and then we want to do some want to read some input. So we are going to end the program, return to the runtime, until the program performs the input operation for us, and then restart the program from either C or D based on the input you just read. And this is exactly what Haskell does, and this is actually real Haskell. This code doesn't show you much because it looks quite imperative, but this is just syntactic sugar for the following. So these two main routines are equivalent. The main function returns a value of something called an IO type. And that value is constructed with a function called bindIO. And bindIO constructs values of the IO type from a pair of things. First, the operation getLine that we want the runtime to perform, and then a new entry point to the program. And we return the IO type to the runtime, our program ends, but after the runtime performs the IO operation, it's going to start our program, restart our program from the new entry point we've given it in a state that depends on the input, right? Depends on the value of Z. There is actually a bit more going on here to make this kind of programming more convenient to use. These IO values can be combined in a nice pattern with these two functions, return IO and bind IO at the bottom, and that's called a monad. So the IO type is a monad, and that allows us to combine those operations in a nice, convenient way and gets us this nice do notation that is more friendly. But if you're using classical imperative programming language like Java or C or Python, in those languages, the meaning of an operation, such as a subroutine application, is not similar to a math function. If you're interested in programming language theory, you may know it's something called a predicate transformer. It doesn't really matter. The important thing here is that the outcome of the operation does not behave like a function. If you enter the operation at one state, there can be more than one state that you end up in. So it can model non-determinism directly. And that is why in Java you can write code that looks like this. We just call readline, and readline is non-deterministic. It does not behave similarly to a function, and just then print the results. And so it's quite surprising that if you look at the Java standard library, and Java is a language that does model non-determinism easily and directly, we find this interface, this class called completable future in the standard library. And I've translated the signature of the methods to Haskell notation, and you can see that those are the exact same signatures as return IO and bind IO. And that's a bit weird because we've just seen that Haskell must do this because that's the only way to model non-determinism in a deterministic language. But Java models non-determinism directly, so why do we need it? So there are many different things you can do with monads, but this is actually used to do I/O. So why do we need monads in Java to do I/O? That's because there is something else going on here, and it's not just non-determinism, and it's not just theory, but the reality of software. The part of the code that performs certain kinds of computations run on the CPU. But when we want to do I/O, we need to move off the CPU and to use a different circuitry in the computer. We basically need to release the CPU to do other stuff, and we call that blocking. What readline does is that it also blocks. It stops using the CPU, it asks the operating system to do I/O for us, using other circuitry in the machine, and when it's done, we ask the operating system to schedule us back to a CPU call when one becomes available. This is done using processes or threads, and we've all learned back in kindergarten that blocking threads is bad because threads are big and heavyweight and expensive, and you can only have so many of them, and blocking is slow, so we shouldn't do that. So it's not because of the semantics, the meaning of the language, that we use that strange monad, but because we just don't want to block, because the implementation in the kernel is unsatisfactory. And so we are using a similar mechanism taken from a completely different paradigm to solve a different problem. So let's look at this Java method that does some important financial computation, and it uses microservices. So every time I call compute, I actually go over the network to call some microservice. I pass in a string the operation I want to perform, some arguments, and I'm going to block and wait until I get the result, and once I get the result, I continue with the state at a state that is based on the result. So, sorry. If we want to use completable future in order not to block, then the code would look like this. It's made of several blocks of computation, represented by those lambda expressions with the small arrows, and those you can think of them as deterministic pieces, but they're glued together with these completable future operations. And this is called asynchronous programming. Sometimes some styles of it is called reactive programming, but it's really just a style that is meant to allow us not to block. There are several big problems with this style. First of all, suppose that the original method was not that simple, but actually want to do some control flow. We want to branch the results of the first compute and to loop over the results of the second one. We simply can't do that when we use completable future, because they are glued not by ordinary sequential composition of Java, but they're glued with this then compose thing. We can do those things using a special API for completable future, DSL of itself, but that DSL would mirror the built-in capabilities we already have in the language. So this already shows some kind of mismatch between this style and language. Another problem is what happens if you have an exception? Right, so normally we use two exceptions giving us some context of where the problem happened in the form of a stack trace. But when we use something like completable future, each of those sequential deterministic pieces could be running on a different thread. And so the stack trace would not give us, and that thread could be different from the thread that actually originally called calc important finance, the main method. So this stack trace will not give us the actual context. And this makes debugging the code hard. Not only that, it makes profiling the code almost impossible, because profiling also works by sampling stack traces. So if the stack traces no longer give us the actual context of the computation, they're basically useless. But the biggest problem is the return type. So like in the case of IO and Haskell, there they have no choice and there they like it. They think it's better. But here the return type is of this strange completable future class that wraps a double. And the double is the actual value we're interested in. And we can't extract the double value from inside completable future unless we block. And that is precisely what we don't want to do. So everyone who calls this method must also continue working with completable future, and it's viral, it infects the entire call stack. So you either work in a world that's entirely asynchronous using completable future or similar frameworks, or you write simple blocking code. And these two worlds don't mix. We have the synchronous world, the asynchronous world, and they don't mix well. So the developers are then faced with a choice of either writing simple blocking code that uses the core abstractions of the language, gives us the right context, easy to profile, but then it's not scalable because the implementation of the threads in the kernel is too heavyweight. And the kernel can support only so many active threads. Crucially, it can support far fewer active threads than it can concurrent open I/O channels. Or we can write in the asynchronous style that is scalable, but comes with a very high cost, as we've seen. Right, so what do other languages do about that? C# introduced something called async and await. The task type in C# is very similar to completable future in Java, but now you can add this async annotation to a method returning task, and you can prefix calls to such methods with the await keyword. And so this code is nice looking, and it solves the first problem. We can use exceptions, we can use control flow, branches and loops, etc. But it doesn't quite solve the second problem, because each one of these lines could actually run on a different thread. And if we get a stack trace, it may be confusing. This is actually something that they've solved in .NET Core, I think, 2.1 release last year. They artificially generate a stack trace that does capture the full context, but it's still very different from the one we would get if we wrote the same code just blocking. most importantly, it doesn't solve the biggest problem. You still have these two separate worlds that can't interoperate. You either block and then you pay in performance, or you don't, and they don't mix. A similar solution to this was chosen by JavaScript, Kotlin, C++, and Rust. I think we'll see why some of them have chosen this. I don't know actually about C# and JavaScript, but the rest will understand. Now, how does this work? What is it that they do? So the compiler takes this block of code and separates it into the same pieces we saw before with the calc and important finance, and it basically compiles this code into that code. It just does it behind the scenes. And you often hear people say that this transformation compiles the async function into a state machine, where each lambda expression is a deterministic sequence, and every composition or every await statement takes us back into the non-deterministic world where there are no transitions there. And what they mean is that the state, why do they say it's a state machine? The state of this method, it's become to be called coroutine. So the state of coroutine is stored, so it's local variables and its instruction pointer where it is stored somewhere in memory, and we can then return to the caller, and if we call that coroutine again, we can enter at a different state, right? Because if we stopped at B, we did some I/O, but then we can call that coroutine again and start from either C or D. The key is that this compilation is different from the ordinary compilation of ordinary subroutines. And that is why the block is a different syntactic construct from an ordinary subroutine. It must be marked as async. You're either a subroutine or a coroutine. Those are not the same, and you must pick. But that is a little strange, because consider how we ordinarily compile subroutines. If it's state B, we make a call, an ordinary call to some library I/O routine. We also need to leave our own subroutine. And when the I/O routine ends, it returns some value, and we go back to our subroutine, and we continue from either C or D. So every subroutine is already compiled into a state machine, or else it wouldn't support returning. In other words, subroutines are necessarily already state machines. So when we say it compiles subroutine to a state machine, that's unnecessary because it's redundant, because all subroutines are always compiled into state machines. So why do we need to separate the two worlds? Why do we need this additional special construct? So one answer takes us back to where we started. A specialized construct is in line with the zero-cost abstraction philosophy, where we have different constructs for very similar abstractions to allow very fine-grained control. And indeed, there are cases where if the compiler knows in advance that we want to use this special construct, this coroutine, it can do some clever inlining to avoid allocating memory for the state, but that is actually the exceptional case. Most of the time, if we have a server request coming over the wire, most of the time it's not going to help us. So you could say that is perhaps why C++ and Rust went that way, but it's not the entire answer. The rest of the answer is that in addition to design philosophy, there are technical and implementation constraints that limit our choices. So if we want to use the ordinary compilation, the ordinary representation of subroutines as state machines, then first of all, we need access to that representation. We need to know how the compiler stores the state of a subroutine on the stack. And this is just not available to us when we are targeting the JVM, JavaScript, or LLVM. So we just can't do it, not without a lot of work on those platforms. Secondly, that representation is platform dependent. And if you only have one compiler, but many different backends, you need to do this work because the representation is different for each backend, for each architecture. We would need to work harder. So it's just harder to do it. So it's easier to do it as a separate construct. Finally, because our goal is to replace the implementation of threads and to do something more lightweight, the standard representation for subroutines is in a contiguous stack. But so the kernel allocates a fixed size stack, which is rather large, for our ordinary code. But if we want to reuse it for something like weight, we need some way to resize that stack to make it smaller or larger. And that means that we need to reallocate it and move it. And this can be difficult in languages that may have pointers pointing into the stack, like C++ and Rust. There are solutions, it's just harder. But in Java, the VM does have access to the internal representation. Actually, it controls it. We have a funny constraint is that we do still need to do the work for every backend, for every architecture. But if we just wanted to do the change to the compiler, we actually have, so in the OpenJDK, we have 3 compilers called C1, C2, and Gual, and an interpreter. So we would have to do the work in at least 4 runtime engines. So it's as much work as doing it on the back end, even more. We don't have pointers pointing into the stack, and besides, we have a GC, precise GC, we track all pointers anyway. And we rarely call into native code that relies, that could have some pointers. And if we just say that we don't support blocking while you're running native code, it's no big loss because very little Java code actually calls out into native. So the imperative language that we know not only handle input and non-determinism, they have this built-in notion of threads of processes and blocking, and it is a good abstraction from a programming perspective. So the only reason why we sometimes want to avoid it is because the implementation by the kernel is too heavyweight. So why do we want to abandon something that's not only a good abstraction, but a core abstraction of this paradigm just because of an inadequate implementation? Moreover, there's a lot of code that's already written in this way. So it's the right way to do it, and most of the code already does it. Why introduce something new? So the more obvious solution, if we don't have the limitations I showed before, is instead of changing how we program, is just with a new implementation. And that is a solution that was chosen in languages like Erlang and Go, and what we are trying to do in Project Loom. So as part of Project Loom, we've implemented continuations in the JVM exposed as this class here. This is partial and from a prototype and subject to change. It is similar in functionality to async and wait coroutines, but it does not require any special syntactic representation. So any code can run inside a continuation. So what we see here, we have a constructor taking a body. That's the piece of code that will be able to suspend itself. And then we need a way to run it. And then it starts executing. Then it can either run to completion, in which case it returns to the caller of run, or it can yield. If it yields, it also returns from run. But the next time you call run, it will continue from the last yield point. We can query whether is done, whether or not we've run to completion. And the scope, I'm going to briefly mention that later. Now, continuation are a very low-level construct. Application developers are not expected to use them directly. They will be hidden. They're supposed to be using higher-level constructs on top of them. But if you were to use them directly, this is how you'd use them. So here we have a loop inside a continuation that loops forever but occasionally yields. And then from the outside, as long as we're not done, and because it's an infinite loop, it's never going to be done, it's going to call run on the continuation. And every time, it's going to return to run after having printed after and before, going through one iteration. The important thing here is that the call to yield does not have to be in a specially marked function. The function does not have to be marked as async, and it does not have to be in the topmost method. It can be anywhere at any depth in the stack. So the continuation maintains its own stack and its own instruction pointer where it is in the program. To be more precise, if you're interested in the theory of continuations in the academic literature, the kind of continuations that this class implements is called one-shot, multi-prompt, delimited continuations. And I'm going to explain each of those. The delimited part means that the piece of the code that we can yield and then resume is not the entire program, but just the code that's inside the runnable given to the body. So that body delimits the code that we can yield and then resume. The scope argument allows us to nest and compose continuations. And I believe this is the first implementation of what I call scoped continuation, and in the literature is known as multi-prompt delimited continuations in a mainstream language. I don't think there are any other mainstream languages do that. It means that we can nest different continuations and jump back to suspend not just the innermost one, but however many we want. This is similar to throwing an exception and going through several catch blocks that don't target the exception type all the way up to an appropriate to the appropriate scope that captures the exception. So we can have several nested exceptions, but the yield can say, I want to return back to the one with an outer scope. The one-shot or non-reentrant means that this continuation is mutable in the sense that every time you run it, it is going to run until the next yield point, and then its state changes. The next time when you run the same continuation again, it's going to continue from the last yield point. So you can never go back in time. I will just say that it is very easy to turn this into a many-shot or reentrant continuation that does allow going back in time. So after you have this, you can implement many-shot continuations yourself. Those who are familiar with delimited continuations, maybe in Scheme, maybe OCaml, I think they had something, may be horrified that the return type of yield and run is void. It is very easy to use this to implement continuations that pass values between them, but there is a good reason for that decision, and that is that we wanted to allow for forceful preemption. Again, for technical reasons, if you want, you have some long computation that you want to pause for a while or maybe stop while it is running, we can decide we don't want to wait for the next time it yields, we want to forcefully preempt it. And this being Java, we also have some monitoring. We like to monitor and inspect stuff, so we have some methods that allow us to inspect the stack. Now, as I said, continuations are a very low-level construct, and we don't expect and may not even allow at first end users to use them directly. Instead, we want to use them to implement the existing familiar abstraction of threads. So a thread or process is actually built from two capabilities: the ability to yield, to suspend your code and later on resume it, and a mechanism for scheduling that code when it is runnable to a CPU call. So let's separate the two. So the first capability is provided by the continuation class I just showed. And for the second, we can use the good schedulers that we already have in the Java standard library. Put together, we get a lightweight thread, which we call fiber. The continuation is implemented by the JVM, exposed only as a single class, and the scheduler is implemented in the standard library or even in third-party libraries, so you can write your own. Now, I mentioned that we'd ideally like not to add any new abstractions, and here on the right you see this new class called fiber, but the API is very much in flux, and whatever we do, we will try to make sure that you can treat both heavyweight kernel threads and lightweight threads implemented with continuations through the common abstraction, maybe a common super interface, and maybe even we'll use the same class. Maybe we'll reuse the same thread class for both of them. But anyway, now that we have fibers, we have to find all the places in the JDK that potentially block, and to teach them about this new mechanism. So what kind of things block? So of course we talked about I/O, and we've gone into all the places in the JDK that do I/O and taught them how to work well with fibers. The other case where you can lock is with synchronization constructs, like locks or blocking queues or channels. Those are all classes in Java util concurrent, and we've done the same there. Just so you can look, so all the classes in Java util concurrent, they block through a class called lock support. And normally, if one of them decides that they want to park the current thread, it calls this unsafe.park that just goes out to the kernel and says, please park this thread. But now we can have either a heavyweight thread implemented by the OS or a fiber. And a fiber is a continuation and a scheduler. So first we test, we give them the both named strands. So a strand is either a thread or a fiber. So first we test, if we're an ordinary thread, kernel thread, we go to the kernel. If not, how do we suspend a fiber? We yield its continuation, and that's it. It stops. It returns to the caller. Its caller is the scheduler. The scheduler then is free to run other tasks. When we want to untarg, we test again what kind of strand it is. And if it's a fiber, all we do is that we take the fiber's continuation and submit it to the fiber's scheduler. Say, please run this task again. But what is the scheduler? The scheduler doesn't even know it's a continuation. To the scheduler, it's just a piece of code. It sees this new task. It's going to execute it again. But because it is a continuation, it's going to continue from where we left off. And together we have this blocking behavior. So, with fibers, if we can indeed make them much more lightweight than threads, and we believe we can, you can have as many of them as you like, as fits in memory. Each of those can be only a few hundred bytes or a couple of kilobytes, depending on how much slack you use. Blocking becomes very, very cheap, hopefully essentially free, depending on the user's need. And we can say that it codes like sync, but works like async, in the sense that your code looks the same as before. You can even use existing blocking code. Third-party libraries, written in Java 20 years ago, will be able to run on fibers. But from the perspective of the operating system, there would only be a few threads running. We can do all this without any language changes or introducing any new concepts. You can download our code and build a prototype JDK here. In a couple of weeks, we will probably release an early access binary that you can use without, we want to do it before the end of this month, without building the JDK, but of course, both the API and the performance change a lot all the time. It's in heavy development. And that is it. Thank you very much.
So this is like an experimental addition to the JDK, right? Will it ever end up in the real mainstream JDK, or what's the
schedule? That's the goal.
Or no, how does that look like?
All development of a JDK starts in a branch, and it's like a feature branch. When it's ready, the goal is for it to be merged and delivered in the ordinary JDK. And then it will become part of the standard and be available in other implementations of Java as well. Okay, so thank you.